Okay, so dependency this time. We're actually going to use the same data set so that we can compare our results. Normally we would not do this, but we're going to use it so that we could talk about power. So if we did this with independent t, is not significant. There's pretty much not any evidence that it is a significant effect, or maybe even that we should believe the effect size, because the confidence interval is so wide. Now, let's pretend that we instead ran this as dependent t, and we gave people just sort of a baseline. So the first week, we just observe their behavior and see what happens. And that second week, we give them the cloak and we see what happens. So this is now repeated measures. And we're going to see what happens to that t-test. So the logic of the test, the idea of this null hypothesis and null differences is the same. But we've now violated the assumption of independence because it's repeated. So we have to control for independence and control for the correlated results, basically. And so the denominator is different. Okay. So before it's pooled standard error, and now it's standard error of the differences. It's still standard error, it's just a different type. So dependent t looks pretty different. So this is independent t. So it's mean minus mean over pooled standard error. Dependent, what is this word? It's an N. I don't even know. Okay. Is actually mean differences, which is still mean minus mean, okay, over standard error of the differences. Mathematically, these two things are very different. So before we took those standard deviations and sort of averaged them together and then divided by the square root of n. Now what you actually do for standard error of the difference scores is you subtract. So you get a difference score from time 1 to time 2, and then you calculate standard deviation and standard error on that difference score. Because I only have one n. Still 12 people. They're just tested twice. And this one I have 2 n's, so I have to pull them together. This one I only have 1, so I just have to find a way to figure out what the change was. So a million years ago, when we talked about power, we talked about how repeated measures designs have more power. And they have more power because of this standard error score. It's almost always smaller than pooled standard error. Because I can control for the peopleness. So the weirdness of people being people, I look at their difference scores, not the overall averages. Oh, you're fine. I've banged my knees on those things so many times. So. Now, in R, the code is literally one spot different. Okay? So now we're going to do paired equals true instead of paired equals false. So if you run, this is why I say it's really easy to run this the wrong way, because everything has to be in long format either way. So don't run independent t when you mean dependent, and don't run dependent when you mean independent. So just make sure you understand the research design, or the data collection type, rather, so you don't run the wrong test. If you run independent when you mean dependent, you violated independence and you have less power. So it's actually more likely to make a type 2 error. If you run dependent when you mean independent, you violated a lot of assumptions, all of them, and you're going to give yourself more power. You're going to make a type 1 error. Okay. So don't run the wrong test. So let's look at that. Now you do get different output, and so that's what all this note stuff is. If the data is not already in long format, it's in wide, that's generally how you'll get it. You'll melt it, and this part will be fine. So you see there's no participant number here. So it does require the participants be in order, meaning, 1 through 12 is also 1 through 12 here, if it's stacked. That's the case if you melt the data. Okay, so you don't really have to worry about that. As long as you don't, and it's out here, eliminate an ace. So don't melt the data and then delete NAs, because now they're no longer in order. And actually won't run because N has to be equal on each side. So if you have 12 people here, you have to have 12 people here, or it freaks out. Because it's dependent, expecting the same number in each group, even if some of them are NAs. So always data screen in wide format, because then if you're eliminating outliers or NAs, you've eliminated the whole row. Okay? And then melt when you get to running the analysis. Okay, so that's true all the time. Data screen in wide, melt later. That'll help you keep your assumptions correct as well. Okay. So, and it says there are a lot of reasons here. Don't melt in data screen, because that violates a couple of assumptions. But otherwise, all of my notes aside, the code is changing here as paired equals true. Okay. var.equal is actually not necessary. It does literally nothing for a dependent test, but you're going to run the wrong thing on independent if you leave it out, so I always leave it in. I always type it. So it actually doesn't do anything when paired is true. It kind of pretends like it doesn't see it. Okay, so it won't hurt you to leave it in, is what I'm saying. Now, let's look at our differences here. So for our dependent t, it's now 11 degrees of freedom. So here's my t-score, 3.8, 11 degrees of freedom. It's n minus 1. There's only 12 people, they're tested twice. So it's not number of times tested minus 1, and it's n overall. So we actually have less people, so technically that has less power. Right? More people is more power. But check out what happened. 3.8 p, let's just say less than 0.1. Okay. You can also do p equals, I have 0.003 down here, that's okay too. So look, it's almost double the size, our ratio of good variance to bad variance. And now it would be considered statistically significant. And so even though we have less people in a repeated measures design, you get way more bang for your buck, and they're a lot more powerful. So that's why if you can ever test things with a repeated measures design, I would tell you to do it, because you get a lot more use out of each participant, so to speak. That sounds terrible. It sounds like we're talking about like products, but you get more power. And you can control for the weirdness of people. If you only have tested them once, you can't really control for them being weird. And it's still an experimental design because we manipulated them getting the cloak. Now, effect size does change. Since the formula here is changing, I can't use the independent t formula. So there are kind of two options. They're both correct. One of them is that's a D, averages. So it's mean minus mean, actually over pooled standard deviation. That's the same as the independent t one. Okay. So D averages is the same one as independent t. We'll talk about why would I do that in a second. D differences, I think it's D av, is mean minus mean over standard deviation of the difference scores. So why are there two different ones? And they're pretty mathematically different. The traditional one is d-diff. If you see someone talking in a research paper about D on a repeated measures design, more than likely they're doing this formula. Okay. And sometimes you're not sure, so that's one problem that people have right now, is that we're kind of having this discussion about which effect size is the best effect size. Because this matches the t-test formula. So t is mean minus mean over standard error diff. So d should be mean minus mean over standard deviation diff. The problem is that this overestimates the effect size. So yes, it gives you more power, but it also tends to overestimate effect sizes, the population effect sizes. People don't like that so much because then you're running studies thinking you have more power than you do. And so it's actually at the moment people are moving towards using d-averages. Okay. So d-averages is a weighted pooled standard deviation on the bottom. So this is basically the average standard deviation of time 1 and time 2 because n is equal. mean difference over average standard deviation. So you'll see in a second, that one will match the independent T1. This one will be much larger. Which one should you use? You can do either one, as long as you tell me which one. So if on your homework you just write D, we're going to count off, because which D are you doing? There's two. Okay. So it's DAV or DDiff. Which one's easier to run in R? DAV, practically. Which one do I think people should report? Given some research, I would say D averages. If you ask me which one is traditional, you're more likely to see in a paper, it's going to be DDiff. So there's a lot of kind of push-pull there. I'd probably suggest going with D averages. But I'm going to show you how to do both. So, D.dependent T av. It looks very similar to independent T because they're so close. So it's mean 1, SD1, mean 2, SD2, and there's one in. Instead of N1 and N2, there's only one in. So you just enter it once. A and K. All right, so all I did here was just rerun my means and standard deviations just so I knew what they were. This time, though, it's 12 and 12, so N is actually just the same people twice. I just have to remember that. So it's not two N's, it's just one. And I would just fill those in. Mean, mean, N. It's going to be grumpy at me because it says full precision is not achieved. That's okay. But here's D, so it's 0.70. And then it gives me the confidence interval for D. But check out the confidence interval this time. Okay, so before it was negative to positive. This time it does not cross 0. So that means it's a little more likely that this is some form of effect size. It's not 0. It's really close to 0, though. So we'll see. But it's not 0. And then it says here, T and P values are not given to you because they would be wrong. So one problem with this is like the way that this score is calculated, it calculates independent T, basically. But it doesn't show it to you because that would be the wrong numbers. It would give you this number, and that would be incorrect. So it just says, no, I'm not giving it to you. With a note that they would be wrong. So that's why I said this one's the easiest. It's also very similar to independent T. Now, if you wanted to do D differences, the tricky part is that you actually have to create the difference scores first. And I just can't think of a better way to do this. And it involves some subsetting. So what I've done here was because I'm subsetting, I created a little table to know what the words look like. Because remember, when you subset, it has to be perfectly spelled, just like factoring. And I created myself a cloak and a no-cloak group. So I split them up. You've done this before. Don't remember when, but we've done it. So now I have a data set of one test time and a data set of another test time. They're not different groups. They're the same people, 2 time points. And then I just subtracted them. My difference score is mischief minus mischief. Okay, so DV minus DV. And now I have this difference score. Effectively, what that is how different they acted from when they had the cloak to when they didn't. So this is how many extra mischievous acts we're getting when I have the cloak, because I put cloak first. So positive scores mean more mischievous, negative scores mean less. And I'll just calculate the mean and standard deviation on that. Okay. So all of these things we've done before, just in a slightly different format. So my mean difference score should be 1.25, right? And it is. My standard deviation of the differences is 1.14, which is much smaller than the normal standard deviations. Now I have all the numbers I need. So dependent T diff is mean diff and SD diff. So I would type those in. 125, 1.14. N is still 12. A and K are going to pretty much always stay 0.05 and 2 for us. It's really grumpy about this, but you should get this down here. So I've got my mean difference score, standard deviation, standard error of the difference. and then that t-score that we had here. But d.diff is 1.10. Kind of a big difference. And so the argument is that d.diff overestimates. It will always be larger. Unless they're both 0, d.diff will always be larger. And we don't tend to like overestimating things. That's not a good idea. So a lot of people are moving towards averages. Whoa. So how would I report that? Well, it's very similar. It actually kind of looks like independent t. Now I can say it's significant and it represents a medium effect size, and I just included the little subscript here to tell you which one it is. I would argue sometimes people like seeing each level's means separately. Some people like seeing mean differences. So you'll see the reporting of these statistics will vary. Sometimes they'll report just like this, means for time 1, means for time 2. Sometimes they'll report it as a mean difference score, so they've already subtracted. The nice thing about showing me the mean difference score is I can check if this is correct. If you give me mean of time 1 and mean of time 2, I actually can't. Okay. Because standard deviation of the difference scores is not SD1 minus SD2. That's not how it works. Now I can check if your p-value is correct, but I can't check if your t-scores are right. All right, so let's try Gpower one more time. How many people would I have needed? It was significant. I had 12 people. How many people would I have actually needed? And so this is coming back to types of tests have different powers. So the first test we needed 68. And really all we're going to change on this one is the type of statistical test. So matched groups. And I think on the next slide I filled in 0.7. And I got that I actually needed 19 people. If you fill in 1.10, it gets even smaller. But for independent t, we need 68, so 34 in each group. For dependent t, we only need the 19, and that's power. So differences in the same effect size, so 0.7 on both of them, differences in the types of test. So trying to hold everything else constant. Repeated measures has more power. So that's why repeated measures is awesome. I'm a fan. Let's put it that way. Something you were afraid you were going to see again, but it will definitely not escape all years, graphs. So bar charts, the nice thing about bar charts is it doesn't matter which type of design you have, they're the same. So you just have to make a simple bar graph because you only have one x and one y. And I copied this code from last week's notes. Or not last week, but y'all know what I mean. Chapter 3-4's notes. Oh, this isn't going to have ggplot. Dang it. Sorry, I need to install ggplot real quick. Hopefully that means HMIS won't be dumb today. All right, there we go. So now mine should run okay. There we go. So I've got my cleanup code. It's the same code from the last one, just cut and paste. Okay. So for my bar graph here, I've got ggplot, dataset name, comma, aesthetic, x, comma, y. So this is where it's going to start to maybe try to keep it straight that if you're running a statistical test, it's y tilde x. If you're making a graph, it's x, comma, y. Unfortunately, that is not consistent across different packages in R. If it's got a comma, x is always first. So a lot of times plots are x, comma, y. If it's got a tilde, y is first. Sorry, it's one of those things. Okay. And then we're just going to use our stat summary, the simple stat summary, where we only have one set of bars. And then I've got x and y. names cleaned up. Oops, it's going to be unhappy. There we go. So you should get a graph that looks like this. So one warning about graphs is if you're going to fix these labels here, make sure you know which label is which. You can't just relabel them. So let's say I didn't like the way these looked and I wanted to relabel them. Cloak is still always going to be on this side. So you have those means from running the means at the very beginning. So make sure the graph looks right, because it's very easy to relabel the labels and think that the graph is switching, but all it's doing is relabeling the labels. Okay. When we get to ANOVA, we'll talk about how do I actually reorder the bars in a different order, because moving the bars around and relabeling are different things. It's kind of a warning. So here's my pretty graph. Yay. So either way, it does look like the confidence intervals overlap, because confidence intervals are calculated based on just each group by itself. Okay. They're not calculated based on independent, like it doesn't account for the fact that these are repeated. All right, so we're going to end actually with data screening. I know we should have started with data screening, but it makes a lot more sense at the end. So independent t, dependent t are parametric. Everything we're going to do is parametric. So based on the normal distribution, so the sampling distribution has to be normal, which in dependent t means the sampling distribution of the the sampling distribution of the differences. It has to be normal, not the scores. Data has to at least be interval. So really, how do I deal with this normality thing? I have at least 30 people. Okay, so repeated measures are great, but n equals 30 is still kind of the magic number. For independent t, not dependent t, just independent t, we've got homogeneity. So homogeneity is that the variances between groups are equal. And for that one, you can look at your residuals chart. We get to ANOVA, we'll talk about how to test this even better. For dependent t, there's actually not a homogeneity assumption. We'll still have you look at data screening wise, the homogeneity, like the chart, but there's actually not one for dependent t. Okay. So kind of in plain English, stat ease, right? Accuracy, missing, and outliers are dealt with. That's always true across all tests we're going to talk about. Independence, so that really amounts to doing the right test. Don't run independent when you mean dependent, and vice versa. Normality, hopefully you have a big enough sample. It should still be linear. Homogeneity and homoscedasticity kind of depends on the test, but it doesn't hurt to look at them. What you'll notice is dropped off is additivity, or multicollinearity. Right? So additivity is the good name for it. There's only one DV, so there's no additivity problem at all. So additivity only matters when you have multiple IVs or multiple DVs. Even if I have a repeated measure design, it's the same people, I expect them to be correlated. And the only time it blows up is if they're perfectly correlated, meaning they have the exact same scores in each column. Nothing will run then, because you're dividing by 0. But you don't really check for additivity. So that's the one that's kind of going to disappear in this section. So what do I do if these assumptions are broken? Well, this is actually an entirely different class, but I'll give you some ideas. So most common problem is homogeneity, where the group variance is wildly different in one group over another group, especially if n isn't equal. So if one group is twice the size of the other group, it's really hard to match variances. Okay. So you can adjust for variances using the Welch test or Satterthwaite test, 4 degrees of freedom, and that's where you actually set bar not equal to false. And also, I told you to leave it as true. We're going to assume equal variances just so we all get the same answer. But if you set it to false, it will run a Welch correction. And your degrees of freedom will be like 12.25. It looks weird, but it corrects for how unequal the variances are. So if your variances are equal, it actually doesn't really do a whole lot to your degrees of freedom. If your variances are wildly different, it will reduce your power. For a dependent test, you can also do a Mann-Whitney U or Wilcoxon rank sum test. For independent t, we can also do a Wilcoxon signed rank test, slightly different things, same dude. Those are non-parametric tests. They do not have normality or linearity assumptions. For robust tests, we can bootstrap, or some people suggest trimmed means. I don't really support trimmed means, but it is an option that people do. So it's, what is that last slide say? Oh, these are good tests when there's no linearity or normality. Sorry, I was like, what do I have written down here? So this is really good for small samples, because non-parametric tests work better when you have kind of a messy set of samples. If you have a large sample, non-parametric and parametric tests become equal, so most people choose parametric. Because it's easier to spell t-test than it is Satterthwaite. So